Recorded. Oh, this is. Oh. Hell yeah, I'm sending that now. Of course I am. What else would I do? Damn it, forgot my water bottle. I'll be back in a second. Better flip it to chat before I start doing other things. Voice hangout. That. No, I need to be in the regular voice hangout so I can answer questions. Yeah. Now where is that water bottle? I have an idle screen. I ought to be using it. Okay. Now the real fun will start. Hello, my name is Nelsnader. Today, we're going to have some fun where I'm going to try a new segment called Professor Nelson Explains. Today, we're going to try by starting with power electronics. Do you know what power electronics are? Power electronics are really fun. So, the first thing to sort of understand about power electronics is a lot of what they do is they transform voltage levels between things. Hello, Blockio, how's it going?
It's going good.
Professor Nelson is in class and he's about to teach you a couple things. Are you ready to be taught?
Sure. I need to work on a video script for uni later, but it's 2 a.m. It's time zone shift tonight. I've got 4 hours to kill.
Do I want plus 3 volts? I want plus 3.3 volts. Okay, so a standard thing that'll happen is you'll have your two sections of the line. You'll have a 3.3 volt load that you need to supply, and you'll have your 5 volt power supply coming off the other side here. A lot of times when things run off like USB or when they run microcontrollers, they need 5 volts. And you'll need to convert down to 3.3 to like run some LEDs or to run some other sort of like chip that's also a part of your microcontroller. Or like another chip that's on the device that'll do some sort of specialized function. Like generally I think CAN is at 3.3. But the point is like you'll need to convert down from 5 volts to 3.3 volts. So the...
Oh, hello, Witch.
Hello, Witch. The easy way...
My stream just died. Amazing.
The easy way to make this happen is to use a resistor divider because it's an entirely passive circuit and it works. It works really easily. The easy way to figure out like what sort of voltage you need across this is you'll do like a division of the voltage, sort of like what's going on here, and then you'll multiply that by the total resistance that you intend to put into the circuit there, right? So you'll end up with like 330 where, so
Okay,
I suppose
my
I ought to be
Twitch
using
seems
like
to have died
actual...
Entirely. I don't see a thing you're doing because
Wild. Which, can you confirm, is it going to Twitch?
Yes, there's just a hell of a stream delay.
Well, that's expected.
this is what my screen looks like right now.
There'll be a picture and voice to
My
text.
Twitch is dead.
Your Twitch
Oh.
is dead. Alright, well I'm going to keep going because I'm here to teach. Alright.
Actually,
Have you
no,
tried
my
refreshing?
download is dead.
Well, point is, we're looking to find out a resistance here for what the resistor would be across like this 3.3 voltage leg here. So what we're going to do is we're going to take like 500 ohms, like that's a reasonable amount of resistance, and then we're going to divide our expected voltage by our like lead voltage or supply voltage, and we're going to end up with 330 ohms there. So what you would end up doing is you would put a 330 ohm resistor across the 3.3 volts that you intend to like drop it across, and then you would put a like the remainder of the 500 ohms, a 170 ohm resistor across the top there, and this will be a voltage divider that will get you to 3.3 volts out for your load. But there's a problem with this. The problem with this is that resistors are lossy. they lose a huge amount of power just by, like, the losses incurred by a resistor are...
Is that kind of the point of a resistor? To lose some power so you don't fry the other stuff?
Resistors consume power by, like... It depends on, like... I guess one of the first things I have to explain, I suppose, is the equation for a resistor. So for a resistor, the voltage across it is equal to the current, labeled in I, times the resistance, R. So this is a constant that will work at most all frequencies. It starts to break down once you get to really high frequencies, once you start to take into account, like, massive temperature effects. But for our simple observations here, my finger's on the other side of the page, V equals IR. Now, the power that's turned into heat in a resistor, there are a couple of ways you can calculate that. The easy way is that power is equal to current times voltage. And this is true for just about any device. But since we know that V equals IR, we can also substitute that into the equation for, like, whatever values we end up with that's handy at the time. So if we've got voltage and resistance, we can do V squared over R, and we'll easily be able to figure out how much power we're losing in the device. Or if we've got current and resistance, we can do I squared R, etc., etc. Power is designated in watts. And, not squared, watts. And watts
Screw
is...
you, I measure my light bulbs in horsepower.
You sure can. It's not, like, there's a messy conversion from watts to horsepower, but it can be done. We will not be going into that here, though. But there is another way this can be done, and that's with power electronics. So, the really fun thing is, like, you always want to figure out, like...
That really fun thing kind of makes me afraid.
Look, this is like... Actually, what...
That bad.
This book, I think, was for a senior level college class about power converters. So, fun is relative.
Just gonna dump it on our heads and expect us to understand.
Well, see, here's the thing. The most difficult math that's required in a power converter is a single derivative. That's it. That's all it takes.
Okay, that's pretty easy.
I'm forgetting
Yeah.
what derivative is in English. So far, I've only done math in German.
Okay, so...
Just draw the symbol.
A derivative, like, this is a derivative over time, this d over dt here. That's a derivative.
That thing.
Yeah, the opposite of it is the integral.
You're cutting in and out, Nelson.
I am looking away from the microphone very frequently as I am doing things. What matters most is that my local recording is pure, because I'm going to post this on YouTube for whatever little bit I'm going to get out of it. So,
Oh no.
the thing you need...
So what you're saying is we should behave.
A little bit.
Oh, behave.
So, the way things end up working is that we can store energy, and we'll be able to, like, pull from that and put into that, like, in a continuous cycle, and we'll be able to sort of, like, meet the proper voltage level that we're expected to have at the time, you know? So, how do we store energy in electrical circuits with passive circuits? Wish, you went to school for a sciencey thing once upon a time, right? Do you know how to store energy?
That is... Yeah, store water really high. That's how you store energy.
Alright, Blockio, do you know how you store energy?
Well, what Rich said is one way. Alternatively, you can use batteries or other things I don't know the English name for. Condensators? Is that what you're also called in English?
Batteries are like a electrochemical reaction, and they store it in the electrical chemical reaction. I'm looking for, like, passive devices. Batteries are not passive devices. The words I'm looking for are inductor and capacitor. So,
Capacitor,
I-
that's the thing that
He did say that word.
aluminum sheets, right?
yep. So, what capacitors are really good at is they are good at, like, storing a voltage and storing a potential energy. We want to, like, maintain a current as it's going through. So, I'm going to draw a circuit here, and I'm going to have to, like, explain what all of these things are as I go through. But please understand.
Capacitor is actually what I meant earlier, because in German it's just Kondensator, which inconveniently also means condenser, so I got my words mixed up there.
My pen is putting out a lot of ink, and I am smudging it every time I am touching it, but that's okay. So, this is...
I recommend not touching it then.
Yeah, I know, right? But this right here that I have drawn... The big problem is just finding my hand
I
on this
recognize
page.
some of these symbols.
Right. So, up at the top here, we have a transistor, and the transistor essentially acts as a switch. The switch will be open or closed, and it will control whether current is flowing through or not. At the bottom there, we have a diode. The diode blocks current from flowing through it in one direction, so current can only flow in the other direction. And then we have the inductor. The inductor is going to be the thing that is doing all of the work to make sure that we can make the voltage what we expect it to be. So there are two states of this particular switch here. State number one, I'm going to draw this here. So I have drawn I1 on the figure here. The I is lowercase here. It still means current, but it means AC current. We differentiate between direct current and alternating current by whether it is capitalized or lowercase. Welcome to electrical engineering.
Oh, great.
But this happens when when there is a voltage applied to its gate or base, depending upon whether it's a BJT or a FET. And when the voltage is applied to a gate, it's closed, and it acts as a short circuit from the top level to the middle level here. So current can only flow one direction, where it comes in from the source, goes through the transistor, and goes out to the load. Now, the second configuration, when we have the transistor off, is now going to be noted with I2. So, when the transistor does not have any voltage on it, it opens all the way up and acts as an open circuit. So that 5 volts over on the far right over here, it can't get through to the other side. It's just hanging out there open. But the current is still flowing around on this other side. And the current is still flowing because the inductor has stored magnetic energy inside of it. So what ends up happening is, like, when you remove the voltage from the inductor, it has to discharge its magnetic energy, and it discharges magnetic energy by pushing current out into everything else. Current can only flow if it has, like, a return path to go around in a circle. That's what this diode is here for. It's here to like, close the loop and allow there to be a path for the current to flow so that the voltage can be maintained on the load side. This is a buck converter. We call it a buck converter because it bucks high voltage down to low voltage. But if we rearrange these components, Blockio, what do you think will happen?
Either something good or something very bad.
Well, the cool thing about whether we, when we rearrange these components, is that we can get it to do something different. We are currently lowering the voltage, but what if instead we were raising the voltage? And I need to find...
Oh boy.
I need to find my picture here. Come on, it's in here somewhere. Okay, here are some integrals to show how this is like...
Actually, this is off topic, but have you ever blown up a capacitor?
Not a capacitor, but blown up microcontrollers. That's when things get really fun, because they emit the mysterious smoke.
Magic smoke. Don't breathe this.
Magic smoke? Whoa! Alright, so we're going to draw our circuit here. What if we need to take a very small voltage and we need to make it very large? Well, by rearranging the components, where we'll have, say, plus 3.3 volts here and plus 5 volts over here. Like, you're being fed from, like, a USB device or something, and it's coming off 3.3 volts, but your microcontroller needs 5 volts so that you can run all the specialized functionality within it. Well, that's where the boost converter comes in. I need to figure out where... Boost! Energy drink.
High School DxD joke here.
Boost. Anyway,
I wasn't gonna say it.
so, let's
I see you're a man of culture as well.
let's start by considering the MOSFET again. When the MOSFET is turned on, what it ends up doing is it ends up doing this, where the current flows through the MOSFET and through the inductor. And this ends up storing magnetic energy inside of the inductor. So that means current is flowing. So you're revving up this inductor, you're making it go whoop, super fast. And then what you do is you open up that switch. And then the current has a different path that it has to flow through, noted by I2. I2 will be a current that goes out to whatever your load is, the other side of the device there. So by rearranging these components, we can control what the current going out to the load is going to look like, and by consequence, what the voltage out there is going to look like as well. And the way we end up controlling things is by a duty cycle. The duty cycle is how often the transistor is on versus how often the transistor is off, and that controls the factor that you're bucking or boosting your device by. So on the buck converter, it's a really simple measurement there. So I'm going to write some extra things on there. We refer to this like voltage ratio or this like on-off time as D. I don't know why it's D, but it's D. I don't remember why it's D at the moment. It's been years since I took this class. But for a boost for a buck power converter, you can see that it's just the output voltage over the input voltage. It's really easy to figure out. So in our case of 3.3 volts over 5 volts, that's a little bit north. That's 66%. D in our standard case would be 66% when Vn equals 5 volts and when V out equals 3.3 volts. Because, again, this is simple division. It's really easy to figure out.
Is it now?
Yes. Blockio, you can do division, right? You can do it by hand. You can do it in your brain.
Yes. But
I can do divine dividing.
Yeah.
Not simple dividing.
So the problem is when you
I
get
wish I
to
could do that.
when you get to boost mode devices, because D is calculated a little bit differently in this case, because you have a higher output voltage and you have a higher input voltage. So the way D is calculated, they used to capitalize. I used the not capitalize for this, but oh well. So if you're looking for a ratio to determine how on the transistor is, what do you think the equation is going to be to figure it out?
The amount of time it's on compared to the total time for the cycle.
The time it's on for the total versus the total time of the cycle. Okay.
Yeah, ratio, the time it's on versus over the total time for a cycle, on-off cycle.
Okay. Blockio, what do you think it is?
I think I just took a drink and didn't understand anything you were saying.
Perfect. Yeah. Which is sort of correct here, because the ratio of output voltage to input voltage is 1 divided by 1 minus the duty cycle. That's why it's called D, because it's called the duty cycle. 1 minus D on the bottom side under there. So, that's how you sort of can configure, what your boost... that's how you can control what your output voltage is going to be compared to your input voltage. So that's a lot of fun. Isn't this fun?
Yes.
I mean, it certainly sounds cool.
Y'all have learned a thing today, right?
Yes.
Yes.
So
perfect.
how does this differ from like a transformer used in, like, I don't know, power
system.
transmission in a line?
Well, yes, let's talk about transformers. The difference between these power electronics and those power transformers is those are, like, fundamentally the concept is the same because they're using inductors, but the difference is, like, we have a transistor here that is switching all the time, and this lets us increase and decrease the duty cycle so we can sort of control it depending upon the needs of the circuit. So if the plus 5 volts end up changing, like if your input line ends up fluctuating, you can still get 3.3 volts out the other side because you have an active component that's switching. With a transformer, you do not have the ability to do that.
Rewind the coils.
Yeah, I'm going
easily or quickly.
to draw a picture here that will hopefully, like, that's coming around the backside. Now the problem is I have to remember how to draw a transformer. Okay.
Something optimal.
Plus, minus, V out.
Damn it.
Plus, minus, V in. Okay, so I've drawn a transformer here because this is another fun thing to talk about because we're learning things today, and that's the important thing that matters. So,
I actually remember that.
So the input and output voltage are linked, and there is one constant thing that links the two of them together. The metal itself that makes up the transformer is magnetic, and the magnetic flux that goes through the entirety of the transformer needs to remain constant. That is the one thing that is conserved. And magnetic flux, the easy way to sort of conceptualize it is we have a number of windings on the input side and a number of windings on the output side. So I've drawn that. This is really fun because I have no idea, like, where I am at any given time, and, like, mirroring things with the camera is a whole lot of fun. Look, this entire stream was intended.
Exact ratio of windings on one side to the other side is gonna determine how much voltage is gonna come out, right?
Before we start to include losses, yes.
Yes.
Because you have flowing through everything a magnetic flux. Magnetic fields get called B. I don't think that's the proper letter I should be using for this. It might be like some other letter that we use for magnetic flux. It has a dedicated letter. I just don't remember it offhand at the moment because I wasn't prepared to talk about this. But what ends up happening is your input voltage times the number of turns you have on one side is equal to your output voltage times the number of turns you have on the other side. So, the thing about transformers is since it is always consistent, because it is a passive device, it'll just, like, continually roll through. It won't have that much loss compared to, like, the other nice thing about this is it's just, like, a straight conversion. Like, the output will follow the input all of the time. If you're running a power grid, it's a little bit easier to guarantee what voltage you're coming from. But in the case with our power electronics here, frequently you're running off a battery. And batteries are subject to something called the Pukert curve. So, I'm going to draw a chart here. And this is going to be fun. Voltage and charge. Good. So this is going to be
Sorry, go ahead.
This is going to be for a lead acid battery. And what I'm going to show here, which, like, because I've drawn it poorly, isn't shown particularly well, but it is shown, and that is the thing that counts. So, batteries are nonlinear devices because their voltage is based on the amount of charge in them. And, like, once you get up here to the high range where you're like at 90% charge or something like that, I guess this chart should be reversed, but
Yes.
it's a bit late for that. Point being, when you're at like, I suppose I should put some marks on here. 100%, 0%. So what happens with batteries? If you're at like 100% charge, the battery will be at something. A standard lithium ion battery will start at like 4 point, well, okay. You can be dangerously overcharged, which is a problem, but at this like safe area of T1 here for like the safe charge, you're at like, I don't know, 90% or something like that. That voltage is 4.2 volts. Then down here at the bottom, you have T2. And T2 is where you're at like 10%. And if you drain, like, if you put any more charge than this into the battery, you will cause massive problems. Your battery will puff up. It'll probably explode. You don't want to do that. If you're down below T2 down here, you have pulled too much out of the battery. You're going to damage the chemistry of the battery where it won't be able to, like, recover. What generally happens is, like, a battery will have, like, 2 electrodes poking into, like, a bath of acid or something like that. And then depending upon the energy stored in there, it'll, like, pull atoms off of one of the 2, the anode or the cathode, I don't quite remember which, and they'll put them back on. Blockio's saying anode, I'm going to go with it because chemistry was not my strong suit.
Yeah, that sounds accurate.
But the point is, like...
Until finals, so I should remember something about it.
Yeah, hopefully. You're the one in college right now, not me. You're going to be tested on this, not me. I'm just here to talk smack for like 30 minutes or an hour. It's already been 30 minutes. Isn't that great? But the thing that happens with it is, like, if you pull too much out of it, you'll damage the anode, or you'll damage the cathode, or you'll damage the anode by pulling too much out of it or putting too much into it. So the point is, there's a safe range of voltage that you can operate a battery in between. For lithium-ion batteries, it's something like 4.2 is your maximum voltage. 2.8 is your minimum voltage, and 3.3 is like your nominal middle voltage. And the problem with the Pukert curve here is that, like, there's sort of a non-linear relationship. Like, it's sort of linear between this T1 and T2 time, but the point is, like, it's steadily decreasing over time. So you won't have a constant input voltage when you're working with, like, I don't know, what's going on in your phone with the battery that's currently in there. Like, it'll be fluctuating between, 4.2 and 2.8 over the entire course of the day, depending upon how much charge is inside of it.
I can very much confirm that.
I was hoping you were going to talk for longer because I decided to take a big old sip when that happened.
We noticed. It looked very funny.
Yeah, where I just popped the thing out and then whoop! Anyway.
You were going, well, this idiot is talking again. Better take a big ol' swig, I don't know.
I was hoping it would happen. But, the thing is, when you're dealing with small electronics like this, where your voltage is maybe like 12 volts maximum, you're going to have those fluctuations. When you're dealing with the power lines, it's standard. You're going to have like you're going to have like 180, you're going to have 12,800 volts. Like, they have expected voltage ranges that you're going to be at any stage of the line before it gets taken down or pulled up based on based on the transformer that's in place. And at this point, it's a good time to mention why they do any of this in the first place. So, do you remember what I said about losses in a resistor? Blockio, can you tell me a formula for power loss in a resistor?
I know that it had something to do with the ohms in that, but I don't remember the exact formula. And I don't think I ever knew the exact formula, even though I was supposed to.
I spoke it earlier today. Which? Do you know a way to compute power loss in a resistor?
It was V squared over R.
That's correct. Congratulations. That's one of three ways to sort of look at it. But the real reason why the voltage is crazy high is because the biggest loss that ends up coming through anything is from current. So we'll look at this and we'll see. I need to put a backing on this. Yes. Oh, good. Now you can see my engineering notebook background. Whatever. The point is, by increasing the voltage, you reduce the current that's going through it, right? And the losses in any given line, any given resistor, are the square of the current times the resistance. So any conductor has resistance built into it. That's just sort of a fact of it existing. Like, the only things that don't have resistance over any given length are, like, superconductors that need you to be at, like, minus 270 Kelvin or something like that. And
I hope not minus 273 Kelvin.
270 Kelvin, I said. Like, a lot of them, like, can only superconduct when they're down near absolute zero. But that's not possible in, like, the middle of Canada or Germany or Minnesota. So
I don't know, we're pretty cold.
We are pretty cold, but we're not that cold. So what ends up happening is, since they can't change this resistance, they can change their current value going in. So what they do is they just crank the voltage crazy high, millions of volts, billions of volts. And by cranking the voltage high, there doesn't need to be that much current for all of the resistance in the way to get you to the end of the line. So that's why high power lines are high voltage lines, because that way we can, like, minimize the amount of current in place, so we can minimize the amount of loss that's going through them.
There's also a thing about AC being better at not losing or not having that much losses over a distance, or am I hallucinating that?
Well, yes, sort of. Well, so here's when they tested, when Thomas Edison and Nikola Tesla were having their AC-DC fight way back in the day. The thing about DC voltage is that, like, a direct way to compare current and how it functions is to talk about a garden hose. Because a lot of people understand how a garden hose works, and the same base equations cover what happens in a garden hose there. So what ends up happening with DC, like, imagine you've got a big old pipe, and it's just full. I'm drawing this out right now. I was not ready for this. And it's just full of electrons. So DC ends up looking like that. And these electrons, as they flow along, they have to bump into each other, they collide with the side walls, they induce, like, pressure, they induce loss as they're going through there. So you will have, like, a massive voltage drop due to all of these electrons, like, bumping into each other and rubbing up against the side of the line as they go all the way down the line and get to their endpoint. So not Tesla, the other guy I just mentioned, Edison. So when Edison was showing off DC voltage, what you ended up happening was, like, you'll have, like, 120 volts at his generator or so, but then as it goes out to the first house, it'll be maybe 119 volts, and then the next house will be 118 volts, and the next house will be 117 volts, etc., etc., etc. So you get to the last house, and it's only at 60 volts, and it's barely getting anything out of the power. And that's just because, like, somebody is closer to the generator. The thing that happens with electric current at the same time is they end up switching the direction of the field that's currently going into like the rest of the into the rest of the wires and stuff. So what happens is these electrons, instead of, like, moving continuously down the stream and needing to pump into things, they just get sort of jostled back and forth. And, like, the signal of it sort of going up and down and back and forth means that they get pulled like in very short directions, so they don't end up like what's the word I'm looking for? They don't bump into each other nearly as much. They don't rub up against the side walls nearly as much. Like converting like how it works and why it works into an explanation here is a little bit tough, so I'm sorry if this doesn't quite make sense, but the point
it does.
yeah, like by using AC, a electron doesn't need to travel very far, and therefore it doesn't lose all that much energy from its input line by going all that far. The problem with AC is that at the end of your line, generally speaking, when you're charging your phone or whatever, you need some sort of rectifier that can take
DC.
AC voltage and turn it into DC voltage, which will require a power electronics. Yeah, buddy!
Yeah, like, I remember my physics teacher talking about that stuff. Like, I think it was... And, like, he made us calculate how thick the wire would have to be to transport
Yes.
DC all the way from the north of America to the south of America, and it was something ridiculous. Like,
Yeah, and that's one of the other problems. Like, you
I think
need...
it was like 3 meters diameter or something.
I could believe
like-
that, yeah.
Like, more copper than exists in the world.
Yeah, like that's one of the other problems about like DC voltage. If you're going to maintain a large continuous current, you need a really thick wire to be able to handle it. And that comes from like the electrons bumping into each other, bumping into the side walls, and causing heat anytime they bump into something. If your
Oh yeah, right.
if your line is too thin for the current it needs to support, it'll end up like heating up too much and then burning itself out. There was a test I had to do to prove something to one of my coworkers where he was just like, yeah, well, generally speaking, the equation for heat generated is based on like the frontal area of the resistor, but the surface area of the resistance of the resistor is different depending upon like how big you make it, and there's the cube square law. Like elephants are not very good at like changing their internal temperature all that quickly because they're so big. It takes a long time from the heat of the inside of an elephant to get out to the outside. Whereas for like a person like us, it's really easy for our heat to get out to the outside. So if you dropped an elephant and us into like a freezing pool of water, we'll probably die before the elephant will. That's the summary for that. It's a similar thing with current in a line, but the engineer was confused about whether like the frontal area of the resistor mattered more than the surface area around the outside of it. So one of the tests I got paid to do was to take an 0603 resistor and an 0805 resistor, hook them up in parallel, and hook them directly up to a power supply and just pump as much current as I could into them, even though they were rated for the same wattage, even though they were rated for the same like power and heat loss, to see which one would blow up first. I got paid to do this. It ruled. Engineering is fun. Which says, Nelson is turning into a real American talking about electronics, and suddenly the conversation is elephants. But yeah, what ended up happening, and part of the reason why Blockio was talking about like having to calculate wire gauge, the resistor with the smaller frontal area ended up like boiling in front of me and produced this awful smoke and smell. And what ends up happening is that like there's not enough room for all the resistors to like pile through, so they start to plug up. And like if you got a hose or something and there's too much pressure inside of it, the hose just explodes. Same thing happens with the resistor. The resistor can't handle it, and then it just goes poof. And it was really fun to stand there.
Experience with that.
It was really fun to stand there with a thermal camera and measure like the temperature of both of these two resistors and see that one of them was like 450 Fahrenheit before it started melting. Oh, it's
50, that's...
big.
That's a book title for Fahrenheit 451.
Fahrenheit 451. Yep, that's the temperature that paper burns at.
Oh. It's like...
Hot.
Hold on.
9 over 5. That's 50 times 5,
220-ish.
250 centigrade?
That is 230 Celsius. That's hot.
Somewhere between 200 and 250, yeah. Yeah, it's hotter than water boils at by a long shot. To put it in perspective.
Twice as much as when water boils. That's hot.
Uh-huh. Don't
Yeah,
touch
that-
it, you'll burn your finger.
That's baking temperatures.
It is baking temperatures, yep.
That's cooler than some things I would bake at.
Yeah, I had chicken for dinner, and I cooked it at 450 Fahrenheit, so about as warm as this resistor was before it fucking exploded.
My pizza oven,
Temperature feels on your skin.
Yeah.
my pizza oven, I would happily get up to like 500, 600.
Yeah.
Gotta cook them fast.
Gotta cook fast. Yeah, because temperature, or like the rate at which things cook is related to like how far off it is from absolute zero, or how far away it is from like the temperature it takes for the chemical reaction to start. If I remember correctly, am I saying that right?
Sounds about right, yeah.
Okay, so
I don't.
there's one type of voltage converter we haven't talked about yet. This is a voltage converter that can either convert up or it can convert down. So it can convert, like, it can take a high input voltage and make it a small output voltage, or it can take a small input voltage and make it a large output voltage. So, are you ready for what I'm about to draw here?
Does it have multiple inductors and transistors, and it can just switch up what it's doing?
No, it needs the same three components as the buck converter and the boost converter that I showed previously. There is one configuration I have not yet shown, and it's this one here. And like what sets the buck converter, the boost converter, and the flyback converter, or as it's otherwise known, the buck boost converter, apart is what the shared component is that goes to the central leg between the two of them. And the way this one works is when the transistor is on, you have this first current, this I1 here, which flows around through the top. It flows between like the positive of the input voltage and the ground of the input voltage, and just goes around in a circle like that. And then as soon as you like take the as soon as you unhook the transistor, as soon as you stop applying voltage to it, you get I2 on the bottom side down here. So what ends up happening is like the current keeps going in the same direction that was in the inductor there, so it'll keep flowing around through there. So that's how you're able to like, and you can, by changing the duty cycle of the transistor, you can control whether it's going up or whether it's going down. So, Blockio, what would the voltage ratio look like compared to the duty cycle of this thing, of this monstrosity that I have drawn here?
I was never good at physics.
What do you think the duty cycle would look like compared to the output voltage relative to the input voltage?
I'm sure it works out to a number, but
Right.
I don't know what that number would be calculated by.
So, let me give you the name of this converter again. The name of this converter is a flyback converter, or as it's otherwise known, a buck boost converter.
Is this what flirting with a girl is like? Like, oh,
No,
look at all these
because-
things, they're so obvious.
If this is what it would take to flirt with a girl, I'd be just swimming in girlfriends right now. Nerds would be Omega Chads. But what it ends up looking like is you just multiply the two duty cycle formulas together. Because it's a buck converter and a boost converter, like, slapped together. It's a buck boost converter. So that's the easy way to remember it. You remember what a buck is, you remember what a boost is, and you just multiply them together.
Talk about Gundam.
That's part of the point of doing this, is to, like, nerd out even harder in a field that nobody's really prepared for, so that hopefully they learn like a thing or two and maybe become like more wholesomer people by the end of it, you know? But so
How do I construct one of these things so that I can make the LEDs in my Gundam's eyes change brightness?
You would do that. Probably what'll happen is I'm going to start drawing things. So here's ideally how. So generally, if you buy a microcontroller off the market, what you're going to end up with is like some microcontroller. It'll have a bunch of functions, and one of the functions it'll have is pulse width modulation, or PWM. And what PWM is you'll have like some time interval t here. So you'll have some time interval t, and then what'll happen is you'll define some duty cycle d, and it'll be like a 0 to 3.3 volt output, but it'll only be on for like whatever this d1 percentage of time is. So this first thing here, that kind of looks like 20% or so. So this would be like a 20% duty cycle. So on the other side of it, what you'd see is 0 volts 80% of the time, but then you'd see 3.3 volts 20% of the time. And it sort of averages out to like, now I have to do actual math and calculation, 0.66 volts on the output side of it. Which, like, a lot of LEDs maybe won't turn on at 6.6 volts, but, like, this is just illustrating a concept. And then you could, say, turn it up to D2, which looks to be about 50%. So then you'd have roughly, like, 50% of the total output voltage, which is 1.75 out of 3.3. So what you can do with your microcontroller is you can command a duty cycle to the PWM that would like increase how much voltage is going out of it. And again, this is entirely a it's sort of like a voltage converter what's going on here, where it's just flipping a switch on and off and on and off and on and off. It's that buck converter up to the inductor before it goes out to there. And then what you would probably do, like with an LED, you won't be able to like, you might be able to see it flickering if your eyes like blinked at a speed somewhere near like, I don't know, 20,000 times a second. But yeah, that's what it takes. But
I know, but just the mental...
Right. This is like how, like with a high-speed camera, you can see like LEDs in lamp fixtures flickering, but not with...
Because the grid that powers everything is at 60 or 50 hertz, depending upon where you live, and you can find that 60 or 50 hertz like ripple in like the dimming and brightening of your lights as the three-phase sort of like spirals, churns, never ending. But if you want to be like really sort of kind of nice about it as it's going out to your thing, what you can end up doing. So I guess we're just going to talk about lighting for a bit because that's fine. So over here, I'm just going to draw the face of the microcontroller here. Microcontroller. This is plus... I should say plus voltage instead of plus power, but it's a bit late for that. So you'll have something like this where you've got a pin that's power, you've got a pin that's ground. And what you'll end up doing here is, generally speaking, putting... So, LED stands for something. Blockio, do you know what LED stands for?
Light emitting diode.
Perfect. Do you know what makes a diode work?
It's something about semiconductors?
Yes. Do you know anything more than that?
Diodes. It's the thing about only letting currents in through one direction.
Okay, that's not about like the fundamental function of what a diode is. Which?
Yes, but my
That
my physics teacher explained it like he allegedly knew the guy who came up with it, but he allegedly knew a lot of people he probably didn't know.
Damn, he knew Schottky? Wild.
which knows nothing more to add to this other than like current goes one direction.
Perfect. So,
Like, actually, the point is he said like the guy apparently had the idea for it when he drove his car in on a road in Germany, and the curve was too tight, so he just ended up flying out of the curves. And he was like, "Hey, I can do that to electrons."
okay.
Allegedly, that's how he came up with the principle behind diodes.
I am pulling up a periodic table of the elements so that I can, like, explain this properly, because we're going to be wildin' right here. Are you ready for some fun?
Oh, I
So-
love me some periodic table of the elements. Let me go get
So,
mine.
what ends up happening, like, diodes are frequently made out of silicon, as I've drawn here. I've also put the letters P and N in here because they're very important. Because what we're going to do is, like, we need to introduce, like, a voltage gap between this P and this N side of the silicon here. Do you know what a good way to change the intrinsic, like, voltage level of a big block of an element is? That's right, baby. It's to inject it with elements of a different element, of a different, like, what's the word for here? Valence electrons? Valence electrons. They have a different number of valence electrons. So,
Yeah, that's alright.
silicon on the periodic table is... Just bring it up. Just bring up the periodic table. Actually, that worked fine. Make it big. Yeah. Silicon on the periodic table of elements is number 14. And, excuse me, what that number means is there are 14 protons on the inside. The way electrons end up stacking up in the shells outside of it.
It's 40. It's not Yeah, it is protons. Never mind.
Yes. That's what determines where they are on the periodic table of elements. If it were 13, it'd be aluminum. If it were 15, it'd be phosphorus. Continuing on. What 14 means specifically is that it has 4 valence electrons on the outside of it. These are electrons that can be pulled off by elements that want electrons more, or it can be given electrons by elements that want them less. So, what you end up doing is you end up, like, your fundamental thing here is silicon, right? And then you've got a line and a hole, you've got a line and a hole, you've got a line and a hole, and you've got a line and a hole. So what you start doing is you start to, like, break up the crystalline silicon lattice with other elements. What you end up doing is you'll have, like, 4 silicon sort of around it, and then you'll introduce something like a phosphorus. Phosphorus has 5 valence electrons. So it'll have, like, an extra electron just sort of, like, hanging off right here, right next to it. Or, the other thing you can end up doing is you can introduce a boron to it. And what happens with boron is it doesn't have enough electrons. It's at +3 valence electrons instead of +5 or +4. So there is a lack of an electron there. So what ends up happening is on the P side of the semiconductor, you'll end up introducing a lot of boron, like injecting it into the silicon substrate itself, and that'll, like, take the overall, like, intrinsic voltage, the overall Fermi voltage of this block of silicon. It'll sort of raise it up a little bit, and then on the N side, you'll introduce a lot of phosphorus, so you'll introduce a lot of extra electrons, and it'll just sort of, like, bring the intrinsic voltage of that side down. And what ends up happening is, like, right at the bridge of those two, you'll get this sort of, like, no man's land, like a waterfall, where, like, electrons are falling off the N side and going over to the P side, and this creates, like, an intrinsic voltage there that must be overcome for any current to be able to flow through the device in one direction. So, what ends up happening, what they usually, like, set this up to be, like, a usual voltage for a light-emitting diode is 0.7 volts. And what happens in that point is, like, you inject electrons on one side with enough energy to be able to cross that potential well that we created by doping the silicon up and down. And then as the electron is traveling through this sort of no man's land in the center, it ends up, like, getting hot, and it ends up emitting light. Well, no, it doesn't end up emitting. Okay, so
is this with, like, energy levels?
This is with energy levels.
Okay.
So, what we end up having here is we'll have, like, the Fermi energy level on one side, and we'll have the Fermi energy level on the other side. So you have to introduce at least you have to introduce at least 0.7 volts to be able to get up the cliff here. And what ends up happening is, a lot of times with the, like, current you're putting in, with the voltage you're putting in, it gives too much energy and an electron jumps too high. And then after it crosses the gap, it needs to drop back down into, like, a convenient place for it to be on the other side. So what it ends up doing there is it shoots out a photon, and then it drops into its comfortable energy level. And those photons are emitted by the light-emitting diode as light.
That's cool.
Okay, this is like a Chem 3... a Chem 2 concept. It was a Chem 2 concept for me, and a Physics 3 concept. Like, both those classes ended up talking about. I had to take one of them. I took Chem 2 instead of Physics 3, which was a fucking mistake. But you learn about energy levels, and that's what makes the light-emitting diodes go brrr as it emits your light. We need to go back to the microcontroller thing I drew on here. But generally what happens is, if you're putting 3.3 volts into a diode that's only 0.7 volts, it's just going to immediately get crazy bright, way too damn bright. Too much current will be going through it because it'll be acting like a short. It'll be pulling too much current out of the microcontroller. The microcontroller won't be, like, properly functioning. So what we end up doing is we end up introducing resistors in line to the circuit in series, as it's called, to be able to knock the current down as it goes into the LED to, like, A, reduce the brightness, but also B, stop the microcontroller from burning out because it cannot provide infinite current. So, the standard circuit you will end up with is, I'm going to call this VN. I'm going to draw a resistor, and then I'm going to draw I'm too drunk to tell if I've drawn that the correct way or not, but I am drawing it like this anyway. Okay, so we have our input voltage, Vn, on the side over here by my right hand, and then we have a resistor. God, doing this mirrored is rough. But then we have a resistor in line, and then we have an LED on the other side of it. So, generally, what will happen is that your LED will be some sort of constant voltage that, like, this is the voltage to turn it on. And that'll be usually 0.7 volts. 0.7 volts will be what it takes to turn on your LED and have it on and have it, like, shooting light out all over the place. And then your total equation for, like, what the voltage is for the circuit is you'll have Vn equals I LED times R minus voltage LED, which in this case is 0.7 volts. So this at least makes sense, right? The loss induced by a resistor is the current times the resistance. The voltage across a resistor is a factor of its current times resistance. And so, like, you're going to have the 0.7 regardless of what the resistor is. What this ends up doing by introducing the resistor is it controls how much current gets through out to the LED. And again, you do this because the microcontroller can only supply so much current at any given time, etc., etc., etc. But where this becomes, like, really fun and how this controls the brightness of your LEDs is current is the one thing that controls how bright the LEDs get. So if you increase the input voltage, you will increase the brightness of your LED. If you decrease the input voltage, you will decrease the brightness of your LED. If we go back to the PWM function that I explained, I don't know, like 20 minutes ago, what you end up doing is you have like 3.3 voltage or 3.3 volts or whatever, but it's only on for like 20% of the time. So at the end, if you consider your LED at like a DC source, you're only getting 6.6 volts into the LED. Like over time, average, that's not enough to turn your LED on. But you can turn that voltage up to, like, you can turn that duty cycle up to like 50%, at which point it'll be running at like 1.75 volts DC. And that's enough to supply the 0.7 to turn on the LED and also have another additional volt that gets like turned into current through the resistor there. So that's one of the ways that people control the brightness in their circuit. They will have like a PWM, they'll have their resistors all out in place, and then they'll just sort of like turn up or down the PWM to control how bright things are. Like the Bandai controllers that control like all of those special cycles for how the PG Unicorn turns on or how the PG Exia turns on, where they slowly light up or they turn to the different colors, control the voltage they're outputting at and the current that they're outputting at as well. So yeah, these are like the super duper basic fundamentals of how you control the brightness of an LED and all that other stuff. Isn't that fun? Isn't this great? Electrical engineering rules, right?
I am having lots of fun.
I love how you said that in like a very monotone sort of way.
Because it is technically 3 a.m. for me right now.
Yes, which is
Real
bringing
sad
up
German boy.
which is bringing up another important thing in the chat. This brings to mind for me, blue-violet LEDs tend to have a higher voltage than red-amber LEDs. Is this because the photons associated with the blue-violet light would require a higher energy state to be emitted, or is there something else at play? Yes, it is due to the fact that the, you can buy, like, at 0.7 volts, I could buy a blue LED, a green LED, an amber LED, and a red LED, and I could put them all together, and I could choose what power goes into there. But generally, the blue photons have a higher energy that go into them. They're at a higher energy level than the red lights would be. So, yes, generally speaking, they want to have I think they want to have a higher voltage for those blue LEDs because they expect like the same amount of current to go into them compared to the other ones. Because
from the ones that I'm familiar with, they're all 10 milliamp LEDs.
Yeah, they're trying to keep the current constant while having like this jump. Yeah, okay. So it'll end up going back to this energy level thing I sort of showed here. Their voltage gap ends up sort of like jumping up and down, and the reason why they're changing the voltage that needs to go into it is they're expecting you to put the same resistor in place before the LED so that you're getting that same like 10 milliamps current with the voltage that they're recommending. I think. Like, part of the problem is I have to think on the fly, like, why would they do that? What are they trying to accomplish here? Like, they've solved a problem in some way that I don't entirely know, and I have to walk to a solution for it just from, like, the things I vaguely remember from my head when, like, it's been 7 years since I took a class on, like, here's how energy band levels work. But this is fun
so
to, like...
you were in the same boat as me, except you passed and I dropped out.
Yeah. Yeah, I'm, one of those guys who's kind of a try. Well, I wouldn't say I'm a try hard. Like, college wasn't necessarily difficult for me. Classes have never necessarily been difficult for me until I got to fucking semiconductor devices, which are hell on earth. You have to do, like, you see this page here? We had big multi-step problems. I would fill this entire page with equations and constants to solve the first part of my multi-point problem. There's no guarantee it's even correct. And then steps B, C, D, and E are all based on you getting the correct answer for A. Semiconductor devices is a fucking nightmare.
I can't believe that.
This sounds like some of my maths profs tests that are just awful like that.
Especially when, like, we go back to this stuff here, and what matters in here is, like, the concentration of, like, whatever dopant you have in here, the boron or the phosphorus or wherever the fuck else it is, and, like, depending upon how well it's doped, changes, like, this middle zone here, like, how wide it is into each part of the silicon. And then, in addition to that, like, the number of dopants is something like 10 to the 14, 10 to the 18, or something like that. So you're dealing with these massive numbers, with these huge constants going on there, and if you're not doing the calculation correctly, you're going to end up in completely the wrong answer that doesn't even look close to correct, and it's really hard to figure out where you went wrong.
That sounds like some of my coding tests.
There's a... In my opinion, as an electrical engineer, coding was much easier than solving these fucking semiconductor devices problems.
Definitely.
But at the same time, we were like coding simple microcontrollers, and we started by doing it in assembly language as opposed to doing it in like C or something. So the
Fucking assembly.
what it means to give a problem in assembly language is that the problem cannot be very complex at all, because you have to be able to solve it in assembly language in a certain expected given time. Once you start to get into C and C++ or anything like that, the problems start to become more complex because they want you to take the same amount of time to solve them with a more powerful language. So,
Yes.
Right, you're given a more complicated tool set, so they want you to do more complicated problems.
Yes, exactly.
yes.
Also, if you convert any given program in C to assembler, it's like 60 times as long.
It wouldn't surprise me. It depends on, like...
At least that's what my software engineering prof told me the other day.
It depends on the complexity of your program, how optimized your compiler is, and the sort of work you're sort of intending to do. Like, 60 seems absolutely massive for me, but...
Well, we were talking about whole operating systems. How?
Oh, okay, well, there we go. That'll start to do it. Question from Witch, and we're firmly in Q&A time before I, like, shut this thing down, because, like, I've had fun with this, but we, like, a standard lecture at my university is 50 minutes or 75 minutes, and we've gone past 50, we're getting up to 75 right now, so we're in the Q&A section before I send y'all home, without any homework, because I'm just a fucking TA, even though I've called myself Professor Nelson. But, at any rate,
That's cool.
Witch asks, so, in a diode, if there is a constant flow of electrons from one side to the other, is it possible for the electron source to be depleted if left unused for long enough? There is a, like, constant. There's like a constant. So, if there is a constant flow of electrons, the problem is there is not a constant flow of electrons. The problem is you have to apply voltage to get... Did I just have my power flicker, or did I just blink funny? Hello, is everyone still there?
I'm still here.
Okay, cool. I must have just blinked really funny because, like, the light above me felt like it flickered or something.
The stream briefly buffered for like half a second.
Cool! I might have just had a power flicker, but was short enough that I was able to keep going. Oh god, it just flickered again. Woo boy! Okay, but the problem is...
Oh yeah, I saw it.
Great, cool. The problem is, current is not constant if you do not have an applied voltage. Because, so, this sort of waterfall I described here, you need 0.7 volts of input power to be able to push electrons up over that hill to be able to go through the rest of that circuit. So they just sort of have this, like, no man's land region in here where electrons will sort of, like, fall down it on one way. But what ends up happening is, like, one electron will fall all the way down the waterfall, bump into another one, that bumps into another one, that bumps into another one, that bumps into another, all the way up the line, until it pushes another one to the top of the waterfall. Which, like, on one hand, that doesn't quite make sense because it sounds like there's a free energy thing going on there. But the problem is, the moment you apply a resistor to make some use out of this, it will, like, sort of stop the process from happening because you've introduced all this other stuff happening. And, like, sometimes electrons will just sort of fall down there, but it, like, it evens out with, like, the electrostasis things that are in place. But yeah, the electron source cannot be depleted if it is not, like, hooked up in a line, you know? Like, you only get current flow that isn't like the electrons just vibing against each other if you have, like, a complete loop to go around in a circle. So, like, you can't have an electron source deplete unless it is, like, hooked up to something or there are some sort of intrinsic losses that are sort of, like, pulling power away from it. Like, what might end up happening in a battery is that, like, because batteries can deplete over time if just left alone for long enough, there's enough intrinsic loss just inside any given battery that over time the chemical reaction will sort of start to break down. It'll start to eat away the anode and, like, remove it from existence or dissolve it into the acid that's in place inside your battery. But that's it returning to, like, you know, that's one of the fundamental laws of thermodynamics where you're returning to, like, a chaotic state as opposed to an ordered state.
I hated entropy. I never understood it in school. I think I understand it a little bit better now.
Yep.
7 years later. 7 years too late.
Yeah.
Mood.
Like, you know, you go through a day, you eat breakfast, and then you stand on your feet the entire time, and you get more tired and more tired and more tired, and then by lunch you want to lay down on the floor and just take a nap. That's entropy. All that order you put in the universe by eating food has gone away as you were doing all of your other tasks, and now you are out of energy to continue doing things, and you're just lying on the floor, tired, sleepy, depressed.
Mood.
And
That's what the kids say, right?
yeah, that's what happens internally inside batteries as well. Alright, cool. We're coming up on the 75 minutes, so real quick questions here. Throw them out. Batteries are depressed. Got it. That's going to be our ending thing. That metaphor of batteries being depressed. Anyway, I hope you all had fun in this inaugural episode of Professor Nelson Tries to Teach Power Electronics and gets diverted into talking about batteries and transformers and other electrical engineering things. But hopefully you learned something today, because I sure had fun teaching you today.
Well, at least we didn't immediately derail it into anime.
That can happen in the future. Anyway, have a nice night, everybody. Goodbye.